In today's notes, we're formally introducing Vertex form of quadratics. We got a preview of it yesterday in the notes for transformations because vertex form is all about what transformations have happened relative to the parent function y equals x squared. Vertex form is written as f of x, or y, equals a times x minus h squared plus k. So it directly exposes the three kinds of transformations that we're doing, a, h, and k, to move the vertex with h and k, and then make the parabola wider or narrower with a. So in Algebra 2, the only difference is going to be that you'll have a, and then you'll have 1 over b times x minus h squared plus k. So that b that we're not dealing with in Algebra 1, it'll come back and it'll be in there as part of vertex form and as part of what the transformations are. But for the time being, we're simplifying and leaving out that part. Okay, so a, it tells us two things. It tells us, based on its size, whether we have a stretch or compression. So if the value of a is greater than 1, if you're not familiar, this symbol means absolute value. So basically the number without the sign. So if the number part of a is greater than 1, the graph will look, we call this narrower. And if a is between 0 and 1, so less than 1, but remember absolute value is always positive, then the graph will look wider, which is vertically compressed. And if you want to draw next to it in your notes, this one's going to be tall and skinny, and this one's going to be flat and wide like that. The sign of a tells us if there's a reflection or not. So we know the parent function is positive x squared. So if a is positive, then the parabola opens up, and you can just picture the parent function opening up like that. If a is less than 0, so if it's negative, then the parabola opens down. So it'll be flipped, vertically reflected. And in general, with any polynomial graphs, the sign of a tells you what happens on the right side of the graph. So the fact that a is positive means that as we go to the right, we're headed upward. And that's true for lines as well. If you think about slope, if you have a positive slope, it goes up to the right. A positive quadratic goes up to the right, and then the left side just has to do the same thing. This applies to any level of polynomials. So if you have a cubic function on the right, it'll go up if it's positive. So that's going to be a consistent thing. A always tells us what happens to the right on a graph. The h value tells us horizontal translation. So if h is positive, the graph will be shifted h units. I think we're saying it in terms of what h is. I always struggle with this part because of the backwards nature of how h works and what we should put in notes. So definitely refer back to yesterday's examples if this is confusing. So if h is positive, the graph will be shifted h units to the left. And here I mean positive in the equation, so in the function. The reason I struggle with that is I find it easier to think of it this way. If we have x plus something, so let's put this, x plus h, it's going to go h units left. X minus h, it's going to go h units right. Technically, that's not accurate because the equation says x minus h, so it's the opposite of what h is. I guess let's do it the right way. I just like thinking of what it is in the equation, but if we want to think of h as the axis of symmetry, we're going to shift h units to the right. But then maybe we put a note here that in the equation, it looks like x minus h. And then the graph will be shifted h units left if h is negative. So this would look like x plus h. That way we can clarify that h itself is positive, but in the equation it shows up x minus h. And here h is negative, but it shows up x plus h. K, way less confusing, it just does what it should do. The graph goes up if k is positive. K units up, I wrote that backwards, whatever. You know how k works. K units up. And then if it's negative, it'll be k units down. Great. So that's all stuff we talked about in transformations yesterday. Let's go through this inner part of the notes. In vertex form, y equals a times x minus h squared plus k. That tells us the axis of symmetry h and the maximum or minimum value k directly from this version, which is why I say it is the best version of quadratics. It makes it very easy to find the vertex, easy to graph it. It's really good. So our axis of symmetry is x equals h, remembering that h is the opposite of what we see there. Our vertex is h comma k. So to do some examples, the numbers will help make it actually clearer because that weird backwards h thing. So the axis of symmetry here, we have x minus 2. So the axis of symmetry is x equals 2. And if you get confused on what like it being backwards, remember that this is 2 to the right. So if you think about where the axis of symmetry is, it's got to be at a positive x value to the right of the y-axis. Our vertex, so our maximum value is 4, and then minimum value, because this isn't reflected. Our vertex is at 2 comma 4. For this one, our axis of symmetry is the opposite of this, so x equals negative 4, and our vertex is at negative 4 comma negative 9, where our maximum value is negative 9. So try these two if you haven't already, and then I can go through it after you unpause. Okay, so this one, there's nothing added or subtracted from x, right? There's no parentheses. So that means we haven't shifted left or right at all, and our axis of symmetry is right where it is for the parent function at x equals 0, our y-axis. Our vertex then is just 3 units up from the origin at 0, 3. This one has no y-intercept specified. No y-intercept, no vertical shift specified. So our axis of symmetry is x equals 9, the opposite of negative 9. And our vertex is at 9 comma 0, meaning it went just to the right. It didn't move up or down at all. So if you think of that in terms of a graph, we shifted over here to the right to where the vertex is now at 9, 0. All right, the a value tells us how much to move up or down from the vertex when we move 1 unit to either side of the vertex. And remember, we can also extend that so that here, if a is negative 2, that tells us it's opening downward, and that 1 unit over, we go 2 units down. 2 units over, we would go to... So we went 1 squared times negative 2, so that's why we went down 2. Here we would go 2 squared times negative 2, so we would go down 8 units. 1, 2, 3, 4, 5, 6, 7, so it would be the very next line down here is where we would run into. Okay? Describe the transformations by the a value in each equation. Well, we can describe all of them. So let's describe all changes. First of all, negative is a vertical reflection. So it's flipped upside down. The 5 tells us there is a vertical stretch by 5. We could also say that as 5 times narrower, but vertical stretch by 5 is good. The plus 4 here makes us a shift left 4, and the minus 9 is a shift down 9. So we can describe all the changes, not just the A ones. On this one, we have 3 halves. That is greater than 1. That's like 1.5. So we have a vertical stretch by 3 halves. We don't have a reflection. We don't have a horizontal shift, but we do have a vertical shift up 7. On this one, A is 1, so there are no changes. There's no reflection and no vertical stretch or compression. The only thing we have here is a shift 2 to the left and a shift 1 up. On this one, we have a negative, so that's a vertical reflection. We have 3/4, that's less than 1, so we have a vertical compression by 3/4. And then we have this -6 will be a shift to the right 6 units. So we just did that for all features. These bottom ones are just the repeat of the same problems, but they've split up A, H, and K. So we went through all of those here. If you want to separate them out in your notes, you definitely can. And then the homework for today is practicing looking at vertex form, using it to draw graphs, identify key features, and I think transformations as well. So I'll do one of these, maybe one of each kind, and then wrap up the notes. So our axis of symmetry is at the opposite of that, so x equals -4. Our vertex is at -4, 3, because this is -h and this is k. Our domain is always all real numbers unless there's some kind of restriction given that says it's not. But unrestricted without a word problem or a story or an explicit domain restriction, our domain is always all real numbers. Our range, this opens up. You might want to do the table and graph first to visualize, but I know that since this is a positive a value, that I'm opening up like the parent function. So that means that this 3 represents a minimum value. So 3 is less than or equal to y is less than infinity, would be our range. For graphing, we start at the vertex. So we go to -4, 3 right here. And then we have an a value of 1. So that means we go over 1, up 1, over 2, up 4, 1, 2, 3, 4, and so on. Over 3, up 9, but I think I'm off the graph then. 1, 2, 3. No, I can reach. Great. And then we make our mirror image points here. And we can graph our parabola. For the table, remember that we start with the vertex in the middle, so we'll put -4, 3. We'll go up to -3 and down to -5. And since a is 1, as we go up 1 here, we go up 1 squared here, and it's just a normal growth rate, so we go to 4. And then if we go backward, we also go to 4 because it's a mirror image, and this is our axis of symmetry. Also, you can draw the axis of symmetry on your graph if you want as a dashed vertical line. So that covers that one. And then our one down here, our transformations, we can list them out. So this, from the parent function, we have an a of 7, so that's a. This is -h, and this is k. So that means we have a vertical stretch by 7. We have a shift to the right by 2, and a shift down by 5. And that's that. So that's where we'll wrap up notes for today. If you're confused on anything we did today, go back to yesterday's notes on transformations. That has more detail on all of the information covered here.